Thank you all for being here on the last day of the conference, for staying. I want to thank Claudia for the kind words and also the organizers for inviting me. And I particularly want to thank the organizers for having a perfectly balanced gender ratio in the keynote speakers this year. So I hope this stays for next year too and for the future. So let's talk about games a bit. So currently there are 1.8 billion gamers online worldwide, and about 700 million of them are active in the sense that they spend 3 hours or more per week playing. 48% of those are actually play social games. So now I originally thought that gamers are 12-year-old schoolboys, but then I thought more, and I realized that my mom plays like about 2 hours a day, solitaire every day. So indeed, when you look at the statistics, on average, gamers are 35 years old, and 41% of them are female. So they're relatively representative, much more than with kind of the stereotype goes. So, of course, this new reality has opened new possibilities for research, and on the one hand, we can observe how gamers behave online in these games, and this has indeed been done very successfully by a number of researchers that are here at this conference. But on the other hand, we can actually use this potential and use the interest in playing games and conduct gamified experiments with these people. So this is what I'm going to talk about here. So why do we want to do that? So to borrow actually a graph that Matt Selganic had on last talk at the conference last year in Chicago. The reason is that this allows us to pretty much bring the marginal cost per participant to almost zero, of course, not counting server costs. And this is in contrast to traditional ways to do experiments where we pay them, and even if they're on Amazon Mechanical Turk and we pay them cents, US cents, still there is as more participants come in and we want to do larger experiments, the cost increases. So of course this is not just a question of size. The size allows us to do qualitatively different studies. So we can still control the interaction online within, of course, some limitations. And this is great because experiments are best for identifying causal relationships, and that's why we want to use them. But now we can do group-level experiments. So we can have multiple large groups, which allows us to look at groups as complex systems. And this allows us to study mechanisms such as feedback loops or path dependence, something that we have not been able to do neither with survey data, observational data, or with kind of small-scale lab experiments. So what is gamification? So roughly it's the use of game design elements in non-game contexts. It's mainly used in the industry. You have all been part of it, more or less. This is a diagram designed by Yu-Kai Chu, who is a gamification consultant for the industry. And it very neatly summarizes different ways in which you can motivate people. In experimental social science, we usually assume, not all of us, but most of us assume that the right way to do it is to give them small monetary incentives. But we know that people are motivated by other things. So among those, we have, for example, kind of social influence, the possibility to exert social influence, meaning, desire to have meaning or to have a sense of accomplishment, for example, and so on. So gamification, as I mentioned, has been used in industry, is being used, but also it has been used in natural science, particularly to answer important questions in science. So, for example, computer science, it's been used for tagging images. In biology, games have been used to study the folding of proteins, the design of RNA molecules, and neuron mapping in cognitive science, and then also actually quantum computing most recently. So in social science, there is, I can think of one prominent example of gamification. That's when Axelrod in the early 1980s invited a bunch of scientists to contribute strategies for the Prisoner's Dilemma game and made a contest out of it. So in a sense, that was a game. where you get others to pretty much, participate in a game, in a study. Most recently, at the last IC2S2, David Lazare and colleagues presented their new platform, Volunteer Science, in which they also rely a bit on gamification elements. But unfortunately, they currently don't have the capability to have interactive experiments where there's more than one person. Now currently you can also kind of play a game by yourself or with a bot. So this is actually what I think is the possibility for future research. So here I'm going to present mainly one study based on about segregation. That's a study that was published last year, and it's in collaboration with David Sumter, who's a mathematician at Uppsala University, and some of his collaborators. And later I'm going to talk about another study that we're just starting together with Claudia Wagner and Andrew Mao, who are in the audience, and which is about inequality. And this study is sponsored by the Volkswagen Foundation, and it's going to be more about the potential rather than any results yet. So let's start with segregation. So as we know, segregation is a very prominent, very significant problem we're all facing today. You have probably all seen something similar, like this map. So this is a map of New York City, where every dot on the map is a person that lives there, and the color of that dot shows their race. So you can see clearly there is a lot of segregation in New York City, but that's a problem all over the world, not just there. So Thomas Schelling proposed a model about how segregation obtains that I'm sure all of you are familiar with. But just to make sure we're on the same page, I'll just briefly go over it. So in this model, we have agents who have a homophily, so they prefer similar neighbors, but they wouldn't mind diversity, right? So they're not bigots, they're not intolerant. And if they are in a situation where they're too much of a minority, there are not that many others like themselves, they would move to a place where they feel happier. So let's take an example of this individual in the center, currently unhappy, they're in a minority. So they decide to move somewhere where it's a better situation. But by doing that, they change the composition of their old neighborhood. So some of their old neighbors might decide to move. And they also change the composition of their new neighborhood. So some of their new neighbors might move. So in essence, every single move triggers more moves and triggers these cascades where you obtain an outcome that is much more extreme than any single individual desires. So what Schelling showed was that even if people are tolerant, you can obtain segregation. But subsequent models have shown that even if they actually actively are interested in diversity, you still obtain segregation. So Schelling's threshold function was like that, right? And in this case, we have a strict preference for diversity. So everybody's kind of best off when the world they live in is completely integrated. And even in this situation, we have basically segregation. So these researchers have concluded that public policies that promote tolerance are futile, right? So this is a very kind of counterintuitive result and a bit quite dark, I'd say. So we set out to test this prediction in particular. So what we did is that we have 4 real-time multiplayer games where the score in these games was pretty much following the utility function that people assumed in this simulation model. So we had a threshold function for what we call the same game. That was the traditional Schelling function. We had a diverse game in which there was only preference for diversity, the same and diverse, which there is both homophily and preference for diversity, and a bit of a contrived example where we have kind of a world in which you have a choice between being complete bigot or kind of like completely fetishizing the other. And we used previous models to come up with predictions, pretty much replicating what was being found that same and diverse and same game obtain relatively high levels of segregation. So then what we did is we went to 20 different high school classrooms in Sweden, and we told them that we're going to give them a demonstration, interactive demonstration mathematical model. Like they didn't know what this is about. And we told them we're going to play 4 games. We start with 4 games. And so in these games, so this is in Swedish, but basically, as in all games, your Your goal is to get as many points as possible. The rules will differ, but overall that's the goal. And you're represented with an avatar that has a color and a number. You can move your avatar up, down, left or right to the next possible location that's available. And the number of points you have depends on the number of neighbors of same color as you, where a neighborhood is defined as the 9 nearest neighbors. So you are going to have a game control that allows you to move your avatar and to look at the number of points you have and how to get higher points. And the game what you're interested in is getting the highest number of points at the end of the game, where a game ends after 2 minutes or after everybody has stopped moving. So at the end of these 4 games, we're going to show you the results. Basically, everybody's results, we're going to project them. So in essence, we gave every student a tablet that served as a game control. We theoretically could have asked them to use their own cell phones, but for kind of better control, we decided to have tablets. And so they, as I mentioned, they can see their avatar and they can move it up and down, left to right, and they can see their utility and what's basically current utility, or rather current score. I shouldn't use utility here. Current score, they know nothing about utility. Current score, and then how to get the highest score. Where here on the on the kind of this axis, we have the percentage of neighbors who are similar color as you are, and then we project it on a screen, pretty much like this one, right? Like where everybody was playing on the game. So let me just show you like a replay of one of these games. Here they're playing the threshold function, the original shelling game. And in this case, they very quickly reach equilibrium. And so we actually stopped the game before the 2 minutes were over. So I'm going to stop it now. I don't have time for this. Okay. So in essence, how we implemented gamification here is that we did not use financial incentives. In fact, we were not allowed to pay high school students money. But instead we had this social comparison where they knew that at the end of all the games, they will see their points and they will see everybody's points. We did not use any ranking system. We just showed them in random order. And we also allowed them to communicate, and also the interaction, because it was real time, it was actually very fast paced, as you could see. And so this kind of really made the environment quite exciting, quite talkative. So let's see the results. So here in these plots, in this like gray fuzzy area, showing the results from the simulation study. So that's pretty much the predictions. And the density basically of the predictions, and the dots show the empirical results we get from the different 20 groups that we got. And so as the threshold kind of function predicts, we get high levels of segregation, and indeed that's what we observe. On top I'm showing the level of segregation, and this is the average score. So basically what's the kind of the average score they get, or the utility in the model. For diverse game, again, as predicted, we have only diversity, no homophily, and we indeed get integrated world. For the same and diverse game, however, we don't get the prediction. So as I mentioned before, this was the very kind of an intuitive finding that we still get, the models predict, we still get segregation, but in our case, actually, it was pretty well integrated. And actually the same with kind of surprising findings for the same or different game, because we a priori thought that everybody would coordinate on kind of this part of the utility function, because they could already do it very well in the original threshold function, right? Like where you get segregation. And so in this case, it was a relatively sparse board, so they could just like segregate in different ends, and everybody's happy. But actually what happened is that it only took one individual who decided to be in this part of the utility function to mess it up for everybody else, right? So you have like 2 segregated worlds, and one individual decides to actually prefer the other, and so it automatically lowers the utility of everybody else from the opposite camp. And so in effect, what happened is that they were all trying to coordinate on the alternative equilibrium, which would be a checkerboard, pretty much. So blue, yellow, blue, yellow. And this is much harder to achieve. So only 2 groups managed to achieve it, despite the fact that they could communicate freely. So you might say, oh, we don't really replicate the findings. Maybe the reason is that 2 minutes were not enough for the participants to kind of converge to an equilibrium. But when we look over time, you can see that they very quickly kind of reach equilibrium. It doesn't change that much. So we don't think that's the reason. You might say, well, we didn't pay them, so hence, they were not optimized, they were not maximizing their utility or their score in this case. But in this plot, we don't see that. So this plot shows the number of seconds that the participant stays in a certain position before they decide to move. So the pinker it is, it means that this is a preferred position, they don't want to move out of it. And so here we have on the x-axis the number of different neighbors, the number of same neighbors. And so in essence what we see is that in the games, indeed, people are overall avoiding positions that giving them low utility or low score, and going for positions that, staying in positions that give them high score. So then we looked at random relocation. So in this case, similarly, we plot basically the percentage of people that move out of a certain position with a certain score to another one with a higher moving score. And so usually if there was kind of an intentional movement from a kind of a low score to a high score, you expected to see a kind of a like a pink below the diagonal, but that's not what we see, obviously. So in essence, what we found was that people were moving randomly, and this was undoubtedly dictated by the very fast dynamics of the experiment, because they didn't have time to evaluate the board. But I think there's also something else hidden here in the fact that to be stuck in a position that's suboptimal, you need to not be satisficing in a sense, right? So you have to recognize that there is no better position, and so you want to stay put. And so in this case, people did not have the ability to realize that. But I think also, in real life, often people might, kind of don't satisfy when they're not happy, and might be willing to take like random decisions just to get out of this position. And the predictions for the same and diverse game were that pretty much, agents reach a situation where they're stuck in a suboptimal position, but there's no way, they realize there's no way to improve their utility, and hence, you get this suboptimal segregation that nobody prefers and actually everybody suffers from. And that's not what we observed in the experiment. So indeed, when we replicated the simulation studies with this assumption of lack of satisficing, so you cannot see the board, but if you don't get a high score, the highest score rather, you still move, then indeed we observe that we get now much better predictions from the simulation models for what we observed in the experiment, and somewhat too actually for the same or different game. So to summarize, in this study, what we found was that incentives for homophily produce segregation, but incentives for heterophily and local diversity prevented. So now this is a kind of very common sense finding. It's like, duh. But, as I mentioned, it is actually against what the kind of simulation models have predicted, right? What theoretical models have predicted. And of course, in our setting, there was a very high-paced dynamics, and so this is not a good model of kind of serious decisions such as moving house, but perhaps it's not that far away from what we experience when we, for example, at a cocktail party, at a conference, or in a schoolyard, for example. So what's here, this kind of first attempt to use gamification, what we learned also is that we might have this kind of perverse situation where we have incentives that we did not intend. In particular, in this case, there was this kind of behavior where people interpreted the game as zero-sum, where they thought that the way to get higher number of points is by getting everybody getting lower points. All right, and so usually that's not a problem. There are always some crazy individuals that we learn to ignore. But as we saw in the same or different game, this could be a problem because we predicted this kind of segregated world in which everybody's happy, but it only took one crazy individual to kind of mess it up for everybody on one side of the board, and so that the whole kind of world had to look for a different solution. Right, so that's something to keep in mind when you use gamification. So I'm going to next talk briefly about this new project I'm starting with Claudia Wagner and Andrew Mao, and it's on the emergence of inequality. And the puzzle we're trying to address here is, why do we observe extreme outcomes when it comes to wealth, to income, to power, to influence, to popularity? When we look among each other, we're actually not that extremely distributed when it comes to mental ability, physical ability, or psychological traits, for example. And also we know from kind of behavioral studies very well that people actually in anonymous situations have a strong preference for equity. So why do we get inequality? So kind of the reasoning goes this way. So we imagine a world in which we are interconnected, we are interdependent, and due to behavior and interaction, although we might be quite equal, there might be some inequalities emerging. The problem is that these inequalities could have differential effects on rich and poor, in a way that the poor get poorer and the rich get richer. And so in the end, we could get a much higher level of inequality. And that's what we're planning to study, in particular in much larger groups, right, in order to be able to identify these feedback loops and maybe path dependence too. And in particular, we're interested to look at what happens when certain characteristics that you achieve are visible. So, for example, your wealth or your level of cooperation or your popularity. And when you can observe that, and then you can decide who you can connect with, right? So theory kind of predicts that due to mechanisms such as homophily, discrimination, or preferential attachment, we indeed expect much higher inequality than that we start with. Then we can also look at what happens when you have prominent group distinctions. And especially when one group is smaller than the other one, and especially when this might be correlated with wealth, right? So social psychology predicts that there are different theories developed for this, but they basically suggest that indeed in these cases we can observe higher inequality. And finally, from behavioral economics, we're also interested in looking at what happens when your rewards are relative rather than absolute. So you can think here about like winner-take-all markets or sports context, where, for example, the difference between number 3 and 4 could be a matter of milliseconds, for example, in running, but in effect, the prizes could be, a huge difference. So that's what we're planning to explore, and to put it in a kind of in a game terms, I'm just going to give you like a kind of a funny idea we're having currently. So here's a game that's pretty much a version of kind of a mix between Tamagotchi and Farmville. Some of you remember Tamagotchi. So imagine you're a farmer and you have a crop, let's say corn, and you have some animals. I'm particularly interested in pigs in this case. And your goal is to grow a happy, healthy, fat pig that's gonna win the state fair. And you can feed your pig the crop you have, so corn, but to truly kind of thrive and be happy, you actually need to introduce some variety in the pig's diet. And so you need to trade with others, right? So of course you could exploit others, you can take more than you give, and so your pig might get fatter and you might win the state fair. So this is kind of, of course, we will kind of manipulate different aspects of what farmers see about other farmers, so how the state fair awards are given. This could help us identify the structural conditions that we wanted to test. So we're very early in this process, and of course we're already kind of starting to think about some very concrete challenges about how do we implement this. The example I gave you with segregation, it was a very controlled situation where we had these high school students. They were not forced to be in the room, but of course there's kind of a pressure from their teacher to be in there, and they could not leave in a sense, or it was very rare that anybody left. But once you put this online with larger numbers of people, there's the problem of how do we bring so many people together? How do we keep them? How do we make sure they actually are engaged? And then, of course, there's also the problem of making sure that their engagement and their probability of staying is not correlated with the treatment, because some treatments might be more interesting than others, right? And then finally, also the problem with making sure that their outcome does not affect their kind of likelihood to drop out, right? Because maybe the poor individuals experience the game differently than the wealthy individuals. And of course, there's also the problem of repeated participation, the fact that we have much less control online of who comes and how many times they interact. And so we are collaborating with Science at Home, which is at Aarhus University. It's actually the citizen science platform that was behind the quantum computing game that I showed very early at the beginning. And we're already kind of starting to think about solutions to these problems. For example, thinking about kind of having an event where we invite all the volunteers from the citizens platforms to come together and use it as a social event where they would play a game and then maybe talk about it afterwards, kind of, and reveal their identity. This possibility to, instead of trying to avoid repeated participation, to embrace it and put it into part of the design, where we would have both within subject and between subject designs analysis, where we can, by doing that, we can do this by basically routing newcomers to to the same world in a sense. So we can compare worlds of newcomers and also their worlds with repeated participations. So, so as I mentioned, this is all work very much in progress, and I'll be very curious about your comments and your impressions. And with that, I want to thank you for your attention and look forward to talking to you both now and in the break. Thank you.